This is the last in our series of videos that we need for the AHL additional waves, phenomena stuff. All right. So we're going to be talking about resolution. We'll be looking mostly at circular apertures, points of light, and also possibly diffraction gratings. Well, definitely diffraction gratings here at the end. All right, so that's kind of the goal of what we're going to cover in the next, hopefully, about 15 minutes. All right, so here we go. Resolution is talking about when I have two different images and they are really far away, can I tell that they are actually two different images, or do they look like a single image, right? You've probably seen this before if you've ever been driving at nighttime and you look at a car that's coming towards you from a long distance away, and from a long distance away, it looks like maybe they only have one headlight, right? Or it looks like it's just one bright spot. But then as they get closer, you start to be able to see the difference between the two headlights, and you see that there's actually two of them, not just one. Okay, this is resolution. When you can tell that there are two individual lights, we say that it is resolved, and that's what it means, that you can see the two individual sources. All right, so this applies to stars that are a long way away. It often applies to car lights. It applies to any two sources of waves, specifically light, but it could be any two sources of waves that we're trying to look at. All right, so you look at my image here, and you can see that first I have a situation that is definitely fully resolved, right? These are single slit, right? When we have a single light that is shining from a distance that is far away, it basically acts as a single slit. That light is coming from a very small width compared to everything around it. All right, so you would have two single slit diffraction patterns here, and you would definitely be able to see the difference between those two lights. You can see the central part, which is the bright yellow there, and then you can see the first maximum showing up like that. That's where you kind of get this halo effect around lights that are very, very far away. All right. This is getting a little bit close together. It's just resolved. You can barely tell the difference between the two, right? You can tell that the two lights here are starting to get pretty close together. They're getting so close together that you could almost say that it's one light, except you can see the little itty bitty divot in the middle, and so you probably guess that it is two different lights. All right. The third one right here, there's no longer a space in between, and so it really does just look like one single light. All right. Now, when we talk about this, we do have a scientific way of saying this is when we define something as being resolved versus not resolved. Okay. Now, the way that works, you can actually see it here in this middle one, right? You can see the maximum. I'm going to change the color of my second wave here, okay, so that it's in purple. It'll be a little bit easier for us to see what's going on. So we're looking at this middle one here, right, and that's its packet right there versus the packet of the red one, which looks something like this, okay, and I just copied over so it's a little bit easier to see. All right, the point at which it is just resolved, or that any closer would not be resolved or any further we'd consider it to be resolved, is the point where the maximum of one of those single slit diffractions lines up with the minimum of the other one. And you can see that over here too. The maximum of the purple one lining up with the minimum of the red one. Okay, at that point it's resolved, but anything closer than that, we would consider as not being resolved. All right, so this is going to depend on how close the two objects are. It's going to depend on our distance away from it because of the angle, right? When we're looking at these two things, if we're very close together, if I'm this blue guy here, I look and I see this guy, and I look and I see that guy. But if I'm further away, that angle changes, right? And the angle between them is much, much smaller, which means I don't have to look in both directions as much anymore, right? You can tell that the farther and farther and farther you get away, the smaller that angle will be, and the less likely that we're going to be able to resolve those two as individual images. All right. Now, We do actually have an equation for if we're observing through like a telescope or a microscope or something like that for a circular slit that we're trying to see these two different sources. This is the formula that we can use, right? This theta, so this is my observer. This is assuming that my observer here is observing through a circular slit. So that circular slit, like I say, could be a telescope, it could be a microscope, it could be your eyeball, right? Your eyeball has a circular hole that you're viewing it through. So any of those, that's why we do a circle. You could come up with a different formula for different shapes, but we don't worry about that in this course. In this course, we're just interested in the idea behind it and using it for a common shape, which is a circular slit. Okay, rather than having the up and down slits, we're going to use a circular slit because that's very, very common, obviously, for all the different situations that I mentioned. All right, so in this formula, you've got theta. Theta is the whole angle there. Okay, it's the angle that you have to subtend through to go from the center of one over to the center of the other. All right, now this is important. This is different than your single slit equation because remember in single slit the angle went from the center to the first diffraction. It was only half of it. This one is the whole angle from the center of one to the center of the other. Okay, you've got lambda, which is your wavelength. The wavelength is going to obviously be important here. And then B down here is the slit width. So what is the width of the slit that we're trying to observe it through, right? So in this case, the diameter of the circle, of the circular slit, right? How wide is that circle? Okay, so let's go ahead and consider a question. Let's look at an example, all right? The camera of a spy satellite orbiting at 400 kilometers has a diameter of 35 centimeters. Estimate the smallest distance this camera can resolve on the surface of the Earth. All right, so what this question is saying is I've got two things on the surface of the Earth. How far apart can those two things be and yet me still be able to differentiate between the two, right? So basically, they're asking about this angle. What is the angle? What's the smallest angle that we could use? So let's work through this and see if we can figure it out. All right. Now, the formula that we were given on the previous page was for a circular aperture, which we're going to assume that since it says diameter, is that the angle equals 1.22 times lambda over b. So we can put in 1.22, we can put in the wavelength, which is 500 times 10 to the negative ninth, and we can put in b, right? B is the diameter of our slit, so 0.35, and this we can now plug into our calculator to solve. And I get an answer of 1.74, so theta equals 1.74 times 10 to the 6th power, negative 6th power. All right, so that is the angle. Yeah, pretty small angle, right? Now with that angle, we can now solve given that we know the distance of the satellite from the Earth. Okay, so the distance of the satellite from the Earth is 400 kilometers. All right, so we can find using that, and we'll use a right triangle down here. So we'll take the angle and we'll divide it in half first. And so we'll get that the angle that we're going to use for our trig will be tangent of theta, because I'm looking for the opposite side. And then we've got the adjacent side here. So tangent of, when I divide that in half, I get 0.871 times 10 to the negative 6th equals the adjacent over the hypotenuse, which is 400 kilometers or 400,000 meters. And I get the answer that x is 0.3 0.349 meters. Okay, now when I put all that together, because 0.349 is just that right side, okay, I'm going to go ahead and double that. And when I double that, I'm going to get 0.698 meters. Or if I round it to 2 sig figs, which I could, I think 3 sig figs is probably fine, but it would be 0.70 meters, right? So hopefully this kind of makes sense. This maybe puts some context to this type of question. But yeah, this is definitely an application of what we're looking for here. And pretty cool that a spy satellite orbiting at 400 kilometers above the Earth can tell the difference between two things that are less than a meter apart. Okay. Anyway, cool stuff. Let's go ahead and look at the next thing. All right. Diffraction gratings can also be used to help separate things, right? We've talked about how because of the diffraction grating, the equation for diffraction grating deals with wavelength, and because it deals with the wavelength, then different wavelengths are going to split differently as we go through a diffraction grating. Okay, one of the things that we see as we shine through a diffraction grating is that in the center we do get very bright white light because it's not spreading out in the center, it's just shining through. But in those areas where we start to get the constructive and destructive interference, we do start to see the rainbow of colors due to the diffraction grating. All right, and so there's an equation for a diffraction grating, which is this. This is the governing equation for resolution of wavelengths. R is the resolving power, right? And so this may or may not, probably won't be used in the same way as the last one, but you will need to be able to calculate R's, and a higher R means that there is better resolving power, right? We don't really say with this one, can it be resolved or not? Just because with better equipment, you will be able to resolve it, right? So we don't normally use this to say, can it be resolved or can it not be resolved? We just say, what is the resolving power? And a higher power is definitely a better thing. Now, looking at the variables here, what do each of these things mean? Well, we're usually going to be considering two different wavelengths, okay? So the top here is, the average of those two wavelengths, all right? So you just average them together. The bottom is the difference between the two wavelengths, all right? M is going to be the order of diffraction, right? So this is the first order of diffraction. If I go out, you could see in the image before that there's a little bit of color out here at the second order. So if you go out to the second order, you could put a 2 there, right? And then the capital N is the number of slits that are illuminated, all right? And so this is different from some of the other formulas that we've used, but this is how we would calculate the resolving power. There are, again, there's some formulas and proofs of this, but I don't think that the formulas and the things that it goes through are valuable to us at this point in time. As long as you understand how to use this formula to calculate the resolving power, then you should be able to get a better, you should be able to answer the questions, and you should be able to understand what we need to understand. You know, I'm looking here, just before we go to a couple of examples, I'm looking here at this bright color, right? It looks really bright and easy to read, right? Can you give me any reason why I might look at the second order out here instead of the first order? Because this does include order here. Thinking about the scenario, thinking about the physics, what you see, thinking about the equation, why would I use the second order instead of the first order? Well, hopefully you came up with the idea that the order is right here. If I use the second order, then I'm going to double my resolving power. It makes it actually easier to differentiate. Now, if it's so dim that you can't see it, okay, yeah, that's a problem. But if you can see it, then it's definitely better to go with a higher order of the diffraction. All right. Okay, I think that's enough for this slide. Let's go on to the next one and see how this actually works. Okay, a beam of light containing different wavelengths is incident on a diffraction grating. The grating has 600 lines per millimeter and is 2 centimeters wide. The average wavelength is 620 nanometers. What are the wavelengths of the closest two wavelengths of light that can be resolved by this grating at the second order? All right. So I'm going to go ahead and write down the equation because it already sounds, obviously I'm going to bring this up now, but the keys, of course, is that it's talking about wavelengths, right? So that's the first part of our equation. It also is talking about the second order, which is right here. It's talking about being able to resolve light. So a couple of different things that it's kind of referring to here. So let's go ahead and see what we can come up with for this question. All right. So it says a beam of light. We've got the grating has 600 lines per millimeter and is 2 centimeters wide. So 2 centimeters wide is 20 millimeters. So 20 times 600. That means that I'm going to get 20 times 600. So that would be 12,000 lines. Okay, that's a lot of lines going on there. Okay, it does say we're using the second order, so we'll go ahead and put in the second order here. And now we're going to put in our average wavelength being 620 nanometers. All right, and so now let's see if we can find out what lambda is here. 2.58 times 10 to the negative 11th meters. Now, if I turn that into nanometers, right, that would be 0.0, see, 1, 2, so 0.0258 nanometers. I had to turn it into 10 to the negative 9th, so I moved it twice. So it can tell the difference between some pretty close wavelengths that are very, very similar to each other. All right. So awesome. We didn't need the resolving power there. Wasn't important. We were able to answer the question without it. All right. Let's look at another example. Two lines in the emission spectrum of sodium have wavelengths of 589 nanometers and 589.6 nanometers respectively. Calculate the number of lines per millimeter needed if the lines are to be resolved in the second order spectrum with a beam of width 0.10 millimeters. All right. So again, we'll use the same equation that we used in the past one. We just have a slightly different scenario here. So we'll go R equals the average wavelength over the change in the wavelength. The difference in the wavelengths equals m times n. What information do we have? Well, we know that the average is 589.3. I just added the two together and divided by 2. This is nanometers. We know that the difference between the two is 0.6 nanometers. All right, just subtract the 2 and you get the difference. It is asking for the second order, so we'll put in a 2 for the m. And then we're supposed to calculate, this is going to give us the number of lines. So let's get that first, and we'll figure out where we need to go from there. And I get that the number of lines illuminated needs to be equal to 491. Just going to use 3 sig figs here, that's fine. So if I need 491 lines, and the beam has a width of 0.10 millimeters, the question is how many lines per millimeter are needed? Well, I need 491 lines in 0.1 millimeter because that's the width of the beam and that's the number of lines that needed to be illuminated by the beam. And so that means I need 4,910 lines per millimeter if I want to be able to differentiate these two waves. All right, and that's it. That wraps up this question, and that's enough on differentiation. Sorry, not different, that's enough on resolution. That's